So after introducing the two properties of the A invariant subspace, we will use the eigenvector. We'll go through the eigenvector test for the controllability. So this is the result that the LTI system, that is the pair AB of the LTI system, is controllable if and only if there is no eigenvector of A transpose in the kernel of B transpose. So first of all, try to understand that what is written in the statement, and then we'll go through the proof of this statement. So it says there is no eigenvector of A transpose. Now if there is an eigen, let's say x be that eigenvector, and saying x as an eigenvector, it would be written as A transpose x equal lambda of x, which is associated with some eigenvalue lambda, okay, which you have been seeing as the computation of the eigenvalues also, A minus lambda I to x equals 0, right? Now this eigenvector which is given by x here, it should not be in the kernel of B transpose. Now kernel of the B transpose is basically a linear subspace. So let's write this kernel of B transpose. Okay, this is a subspace, and it says that this x should not belong to the kernel of this B transpose, which is to say that the B transpose x should not be equal to 0. Okay, because if this eigenvector x belongs to the kernel of B transpose, then in that case we would have B transpose into x equal to 0, right? So what we need to show here, that there is no eigen, or let's say there is an eigenvector x which satisfy this equation but does not satisfy this equation. Okay, so this is what we want to show here. So let's see the proof, which says 1 implies 2, that the AB pair is controllable. If the AB pair is controllable, then it implies that there is no eigenvector of A transpose in the kernel of B transpose. Now we'll we'll prove this through negation, that is the reverse implication, that if there is an eigenvector of A transpose in the kernel of B transpose, then it implies that the system is not controllable. Okay, now saying that there is an eigenvector of A transpose in the kernel of B transpose implies that A transpose minus lambda I x equals 0. This is the first equation, and the second equation is this one. So both the equations are satisfied. Okay, so suppose there exists an eigenvalue lambda associated with the eigenvector x with a non-zero eigenvector for which B transpose is equal to 0. Okay, this is the negative statement of the second one. So let's write the multiplication of the controllability, the transpose of the controllability matrix into x. Now here I have used the property of the transpose of the matrix. Let's say we have some matrix M which is given by some n and p. Okay, now if I take the transpose of this one, it would be equal to n transpose and p transpose. Right? So this the same property I have used here, because here we are taking the transpose of the controllability matrix, and it would become B transpose A transpose up to B transpose into A transpose to the power n minus 1 into x. Now I have taken this x inside these block matrices, and we would have the first term as B transpose into x, the second one would be B transpose into A transpose into x. Now A transpose is already equal to the lambda x, so and lambda is a scalar, so we have replaced here by lambda into B transpose into x. Okay, similarly up to lambda to the power n minus 1 B transpose x. Okay, now if you pay attention here, that we already have this assumption that B transpose x is equal to 0. So all these parts would be, it would become a 0 vector which is written by 0. So what does this mean? That x is an eigenvector which is in the kernel of the C transpose, the transpose of the controllability matrix. Now it means that the dimension of that subspace would be at least 1, because we have already assumed that x is a non-zero vector, and for a non-zero vector it satisfies that the C transpose x is equal to 0, and that is to say that x is also in the kernel of C transpose, and which is non-zero. So the dimension or the nullity of that subspace is at least 1 or greater than equal to 1. Now if we use the fundamental theorem of linear equation, I could write if you remember that we have nullity plus rank is equal to the number of columns of that matrix. So here we have the rank of C transpose is equal to the number of columns, which is n, minus the dimension of the kernel of C transpose, which is the nullity. Now here we already know that the dimension is at least having one value. There is no non-zero vector, meaning to say that the rank of the C transpose would be definitely less than n. Okay. Now we know that if we take the transpose of the matrix and if we compute the rank won't change, meaning to say that the rank of the controllability matrix would definitely be equal to the rank of the C transpose. And the rank of C is less than n, which contradicts the controllability, because for the controllability we should have the rank of the controllability matrix to be equal to n. Right? So this proves the first implication. Now the second one, that if there is no eigenvector, or that is to say, or the negative statement that if the system is not controllable, then it implies that there is an eigenvector of A transpose in the kernel of B transpose. Okay. So we will prove this part by using two arguments. The first one, that first of all we will show that the subspace, the kernel of C transpose, is A transpose invariant. Now using the property 2, which is written over here, that the subspace V, which is already a variant, contains at least one eigenvector of A, of that matrix. So then we will use that property to finally conclude that if the pair AB is not controllable, then there definitely exists an eigenvector of A transpose in the kernel of B transpose. Okay. So let's see. So since we know already with the assumption that the pair AB is not controllable, we would have the rank of C, which we can write also equal to the rank of the C transpose, should definitely be less than n. If it is equal to n, then it would have become controllable. Implies that the dimension of the kernel of C transpose would be greater than or equal to 1. Now let's see. If X belongs to the kernel of C transpose, if X belongs to the kernel of C transpose, then the equation 7 hold. This equation 7 is nothing but the C transpose into X is equal to 0, which we had seen earlier. So that equation is number 7. And therefore, we could write that X belonging to the kernel of C transpose implies that, let's denote this vector. Let's say denote this vector by x bar. If you recall the property of the invariant subspaces, it means that if X belongs to the subspace kernel of C transpose, and if this x bar, which is given by A transpose X, also belongs to the kernel of C transpose, then it implies that this subspace, which is the kernel of C transpose, is A transpose invariant. Okay, so I can write this one also, the C transpose into A transpose into X, where this A transpose X would be multiplied by every element of the block matrix. So we would have B transpose into A transpose. So the power of the A transpose would increase by 1 in all the block matrices. Okay. Now earlier we have already seen that all these elements except A to the power A transpose to the power n, X is not necessarily equal to lambda to the power n into X. If it would have been, then it would also be 0. Right? So we only need to show now that this part is equal to 0. If we are able to show that this part is equal to 0, then it means that C transpose into X bar is also equal to 0, right? Which by which we will finally conclude that this subspace is A transpose invariant. Okay, so let's see. Now by using the Cayley-Hamilton theorem, if you recall the Cayley-Hamilton theorem for a given matrix A, if we compute the characteristic polynomial by delta s to the power n plus these elements, then it implies that the polynomial by replacing s by a would be equal to 0. So now using this theorem, we can write A transpose to the power n as a linear combination of the lower powers of A transpose, right? Why? Because it is equal to 0. So it would contain some A to the power n plus the lower order terms. Now if it is equal to 0, I can write A to the power n as the linear combination of the lower order terms. So using this argument, we can use this fact, and since we know that all these lower elements are already 0, which implies that this term would definitely be equal to 0, right? So this is what it says. So X belonging to the kernel or this subspace, we have shown that this subspace is A transpose invariant because this equation has been satisfied. Okay, meaning to say that this vector A transpose into X also belong to that subspace. Okay, so this shows that this subspace is A transpose invariant. Now using the property 2, we then conclude that this subspace, so let's visualize this V, which is already an A transpose invariant, okay, which is kernel of C transpose. So kernel of C transpose must contain at least one eigenvector of A transpose, because this subspace is A transpose invariant. If it contains one eigenvector of A transpose, and since C transpose X equal to 0 implies this would only be possible if B transpose X is equal to also 0, which says that the second statement is also nullified, or we have the opposite of the second statement. So this completes the overall proof of the controllability of the AB pair in terms of the eigenvector of the A transpose not belonging to the kernel space kernel of B transpose. So here there is another result which is I would say the elegant restatement of the result what we had just discussed. So it says that the AB pair is controllable if and only if the rank of this matrix A minus lambda I B is equal to n for all lambda belonging to the set of complex numbers. Okay. Now this test is also called the Popov-Welwich and Hotter's test, or in short the PBH test. So this is just the restatement of the statement what we had said, that the eigenvector of the A transpose should not be in the kernel of the B transpose. Okay, so we can see a quick proof or the equivalence between these two statements. So here we'll show the proof by establishing the equivalence between this rank condition and the eigenvector condition which we had seen in the previous result. So now again using the fundamental theorem of linear equation, we conclude that the dimension of the kernel of this matrix I can write as equal to n minus rank of A minus lambda I B. Okay. Here in fact I have used two properties. The one that the orthogonal complement property has also been used here. Okay. So now if we suppose that this rank condition has been satisfied, so we would have n minus n would be equal to 0 for all lambda belonging to the set of complex numbers. Now again, using the same argument, we can say that the kernel of this matrix can contain only the 0 vector because the dimension is 0. If the dimension is 0, then it would contain only the 0 vector, which is equivalent to saying that the kernel of this matrix, which is given by this set X belonging to the n-dimensional set of real numbers, both these conditions have been satisfied. That is, A transpose X is equal to lambda X, and B transpose X is equal to 0, and it should be equal to 0 because it contains only the 0 vector. Only the 0 vector, which is precisely equivalent to the statement that there can be no eigenvector of A transpose in the kernel of B transpose. Okay, this finishes the proofs. So for the eigenvector test, we have two proofs, two tests given the matrices A and B. Either we ensure that there is no eigenvector of A transpose in the kernel of B transpose, or by computing the eigenvalues of the matrix A, and for all the eigenvalues of A, if this rank condition has been satisfied. And this, it says that for all the eigenvalues belonging to the set of complex numbers. Now these eigenvalues could be stable eigenvalues and could also be unstable eigenvalues. Now if this rank condition is satisfied for all the eigenvalues, meaning to say that your system is controllable. Okay.